Hello, and today we are talking about area. Now, we have estimated area and we have been using geometric shapes for area, and today we will be using calculus to find exact areas under curves, and we will need a graphing calculator to do this. Now, in order to find the area between a curve and the x-axis, we're going to use a definite integral. So we already know how to find a definite integral. We already have discussed the idea of area between the x-axis and the curve, and now we're just putting the two together. So when we're asked to evaluate a definite integral, the value will be signed, meaning it will either be positive or it will be negative, as opposed to when you are asked to find an area, the value will always be positive. And how is that related to an idea in motion? Well, speed is something that is always positive. However, velocity is signed positive for moving forward, negative for moving backwards. So here we are with a shaded area S down here in this diagram. And we are bounded by the line x equals a. So here's one boundary. And the line x equals b. Here's our second boundary. We have our curve, which is f of x, and that's our curve right here. And we're also bounded by the x-axis, which is down here. Before finding the area of this region, what we're going to do first is draw in a rectangle that could be used for a Riemann sum. So we've already done this before. Our Riemann sum, if we drew in a rectangle, and I don't care about whether it's a left, a right, a middle, we just need a rectangle that could represent our Riemann sum. So we're going to draw that in first. Now, once I have that drawn in, I'm going to label the width. The width of my rectangle right here, that is the change in x. That is dx. Now, to find the area of this Riemann sum, I would then multiply by the height of my rectangle, and that would be, in this case, a y value, or an f of x. Either way. So, if I wanted to set up the definite integral to find this area, S, the area of S, it's going to be a definite integral, and my bounds are going to be from A to B. I'm starting at A and I'm going to B, and it's going to be the area of the rectangle. So the area of the rectangle will be the height of the rectangle, which is going to be f of x, times the width of the rectangle, which is dx. Now, I need to point out a few things about this. The most important aspect is your dx. Okay, the width of your rectangle, in this case, is the change of x. At which point that I know this is a dx, that tells me that this value at the top bound must be an x. The value at the bottom bound should be an x. And there's one more thing it tells me. This value here should be a y. But what it means is, because this is f of x, the variable I should see should be x's. So even though our f of x, which is blue or purple, is a y value, the variable that I'm going to see is x. So that's what we just did. In the definite integral, identify each item as an x value or a y value. So we know that our dx was an x as well. I didn't label that one. Our lower bound is an x, our upper bound is an x. So let's go ahead and try one. So in example 1, we're going to find the area bounded by the y equals x squared. That's my f of x. X equals 2. And again, that's an x value. and the x-axis, which is right here. And we're only going to write down the setup. We're not going to work it out. So step one is always going to be to draw the rectangle. Okay, that's going to help you with this idea, area, and additional ideas that are on their way. So if I was doing a Riemann sum for this, my rectangle would look like this. And then, of course, I need to find that my width is going to be dx, and my height is going to be a y value. And this y value I know is right here. That y value is x squared. So first thing I do is I have my rectangle. Second thing I need to do is I'm going to start with my setup. My area is going to be a definite integral. My lower bound is my first x value. And I know that x squared is equal to 0 at x is 0. And you can see that's part of my area here. So my lower bound is 0. My upper bound is also an x value, which is 2. I know that I'm going to be multiplying by my width, which is dx. And then I know that what I'm going to have right here is my y value. And I know what my y value is. My y value is, again, x squared. So just to double check, once I have this is an x value here, I know that my lower bound is x value, my upper bound should be an x value, and my height of my rectangle should be a y value, which means the variable I should see is x's. So that is our setup right there. That is it. Next. In the definite integral, identify each item as an x value or y value, and I did that as we went. Now we're going to try one that's a little bit different. If you need to write something down, pause the video here. So moving on to this one, which is a little bit different. So we are finding the area bounded by y is equal to the square root of x minus 2 of y equals 3 of y equals 1 and the y-axis. So now I need to, again, do the setup of this area. I need to draw in my rectangle. Now, if I draw in my rectangle up and down here, are we okay that I'm not touching the blue curve at all? So I cannot draw my Riemann sum, my rectangle, up and down like this because I never even addressed that there's a curve there necessarily. So what I want to do is draw my rectangle not up and down, but across, horizontally. So now when I have my rectangle, the width of my rectangle is actually now dy, which means the height of my rectangle right here is not going to be y, but it's going to be x. So first thing I did was I draw my rectangle, which I have done, and again, once you're bounded by the y-axis, you're going to want your rectangle to be horizontal. Second thing I need to do is my area is going to be, sorry, I'm going to change my color super fast. My area is going to be a definite integral, and I know what I have as the width of my rectangle is dy. So once I know that that is going to be dy, I know that this thing is going to be an x. And I know that here and here, these things have to be y values. So my lower y value, the one that's bottom, my lower y value is 1. My upper y value at the top is going to be 3. So this is what my area is going to look like. Now, when I plug in to my x, this is to be an x value. I should see what variable? I should see y's, which means I can't just jump in and plug that in right now because I don't know what x is. So I'm going to start what I have, which is y is equal to square root of x minus 2. This is my third step. I need to actually solve for x. So while solving for x, I'm going to square both sides. And that gives me y squared is x minus 2. And I'm solving for x, so I'm going to get x by itself. So I add 2 to both sides, and I get y squared plus 2. So finally, what I need to do is I need to replace x. So my final step, I'm going to kind of jump to the left a little bit, goes right. So now I have my area is equal to, my bottom bound is 1, my upper bound is 3, and again, those are y values. I'm going to multiply it by the width, which is dy, and then I'm going to insert my x, which is y squared plus 2. So again, once my width is a dy, I should see a y value up here, y value down here, and the variable inside, I should see y's. If you need to pause the video to write anything down, please do so now. Otherwise, we're moving on to the next problem. So our next example is we're finding the area bounded by this y value, x equals negative 1.5, x equals positive 1.5, and the x-axis. So I need to highlight a key word here, area. And I need to note that because that tells me that this thing is always positive. Area will always be positive. Now, here is an example of area where we can't just do one definite integral. And why is that? Well, this definite integral will give me something negative. This definite integral will give me something positive, and this definite integral will give me something negative. So what I need to do is I need to find 3 different definite integrals, find the positive version of each one, and then I'm going to add them together. So step 1 is going to be to find where the curve crosses the x-axis. Now I have a beautiful graph here to help me. The points where the curve crosses the x-axis are here and here. That value is at negative 1, and this is at 1. Now, if we didn't know that, we didn't have a graph, which it's hard to tell, sorry, on my screen. If you look down, you can tell that this is negative 1, and you can tell that this is positive 1. If we did not have that, then what we would need to do is we would need to know where y is equal to 0, which would be where 3/4 times 1 minus x squared is equal to 0. I would need to solve for x. Now, this one I don't need to do that because I have it graphically. So where the curve crosses the x-axis is at x equals negative 1 and at x is equal to 1. So from here, we're going to move into setting up our definite integral. Now to set up my definite integral, the first thing that I need to do is draw my rectangle. So step 1, we need to draw the rectangle. I'm going to go ahead and draw all rectangles. I need 3 of them. So my first rectangle is right here. Again, I need to make sure I'm touching the x-axis and touching the curve, no matter where I place my rectangle. Sorry, so my width was dx, and that does tell me that my height is going to be a y. Drawing in the remaining rectangles, again, I touch the curve and I touch the x-axis, my boundary, and I have a dx, and then I will have a y. And finally, I draw in this rectangle, touching the x-axis and touching the curve. I have my width is dx and my height is a y. So now that I've drawn my rectangles, the next thing that I'm going to want to do is I need to then, write down my setups. So for my first setup, I need to have my definite integral is going to be from negative 1.5, and that's my starting point. You can see that my axis, sorry, this axis starts at negative 1.5, and I go to negative 1, and then I'm going to have the y value times my dx, and my y function looks like it's right here. You can probably see it on your paper, is 3/4 1 minus x squared. So then what I need to do is I need to do the same thing for the other two regions. This one, of course, the way I have it written right now is going to be a negative thing. So what I'm going to need to do is actually change the sign eventually to make sure that I take the positive version. Now, if you could please, right now, write down the setup for the definite integral for this piece and write the setup for the definite integral of this piece. Please pause the video now to write those setups. Here are my setups, so be sure that yours are correct. If they are not, please pause the video here to try and tweak yours to make it look like mine. Moving on to number 3. What I'm actually going to do now is say we're going to go ahead and grab our calculator to evaluate each of these integrals. So if you have a TI, you're going to grab your calculator. If you have a Casio, you're going to grab your calculator and you're going to go ahead and evaluate the first integral. So if you would please evaluate just that first integral, and we should get a negative value. So pause the video here to enter the first definite integral in your calculator. Here are the values that I got using the TI and using the Casio. Pushing the FD button, I can change my Casio version into a fraction, and I do have the same value. So what I'd like to do is store this value. So go ahead and on the TI, you're going to press stow, and let's go ahead and put this in alpha A. And we know we put the negative version in there, although when we go to add it up, we're going to want the positive version. In the Casio, right above the on button, we're going to stow this in alpha A. And again, we're using that negative value that we got. Now what we need to do is we need to find the other two definite integrals. So if you could go ahead now, find the next definite integral, and we're going to store that in B, and then find the next definite integral, and we're going to store that in C. So please pause the video here to evaluate those two definite integrals. This is what I got for our second definite integral. Just checking as you go. I'm going to show the next one momentarily. Here I have both my calculators with my third definite integral. So now I'm going to need to actually add these up. So my A and my C are both negative, so I actually want to use the opposite of those. So on my TI, I'm going to do the opposite of A plus B. B was easy because it was positive 1. And then I'm going to subtract C. And again, that's making each of the pieces that were negative positive, getting a 1.4375. Same thing on my Casio. I'm going to do A, but I want it to be a negative A. And then plus B, which again was just 1, and then minus C, because C was negative, I want to make it positive. And I have 23/16, changing that into a fraction is 1.4375. Either answer is fabulous. So all we did there was add the absolute values of each one. So I'm just going to write that down. Add the absolute value of each definite integral. Now, I could have done that a lot easier, twofold. I could have done it a lot easier in two different ways. Sorry, that's what we did right there. So I'm going to do this using the absolute value feature on the calculator. And I'm also going to store the function in y1 so I don't have to continuously enter that. So the first thing I'd like for you to do is in your y1, can you go ahead and key in that we have 3/4 times 1 minus x squared, which I could have done from the get-go and just used y1 over and over again. So again, we're just putting in our function that we have. So now what we're going to do is we are going to do our definite integral again. So go ahead and pull up your definite integral. And we're going to key in the absolute value of our function. So in our original curve, what I would like to have done is I'd like to have gone from negative 1.5 to a positive 1.5 of the absolute value of this. This is what I would like to have done. That would have taken the absolute value of each piece. It basically, what that does, one second, is it's going to take anything down here that's below the x-axis and reflect it so that it's above, at which point it would make each definite integral positive. So what I need to do is I need to put in that absolute value into my calculator. So sorry, I want to put in my negative 1.5 bound. Go ahead and I'm put my bounds in. And then in my calculator, I want absolute value, which is under math, num, and then absolute value. And it puts those in. And then I want to put y1 in, which is in vars. And then y vars, and then function and y1. And then I still need to put in my x right here. And that should give me the same value that I had before. And then in my Casio, I want to go to vars to enter y1. It's a graph variable, and it's a y, and I want y1. Oopsie, I forgot to do absolute value. Option, turn the page, num, absolute value. I hit round. Absolute value. And that's where I want my vars y1. Sorry about that. Now I need my bounds. And I should get the same thing that we had before. Now you can tell the calculators take a little bit of time to think that through, but eventually your calculator will work that out. And again, storing in y1 would make what we done earlier much faster. Okay, so moving on to the next page. We are now going to find the area between two curves, which is very different. I don't have an x-axis or a y-axis to deal with anymore. But when I draw in my rectangle, I need to make sure that it must touch both curves. So for example, if I plugged in my rectangle this way, I'm touching the red curve at one end and the red curve at the other end. That is not what I would like to do. I want to draw in a rectangle that touches the blue curve and touches the red curve. Now it shouldn't matter where I draw my rectangle in, here or here or here, no matter which rectangle I draw in, and again you'll only need one, I should be touching the blue curve and the red curve. And again, my width of this rectangle is dx, and the height of my rectangle is going to be a y value. So this definite integral, I have a boundary of A and a boundary of B. So the area for this one, again, my width is a dx. So I know in here I need to have a y value, but I also know my bounds need to be x's, which are A in this case, and my other bound is B. But to find this y, I basically need to take the top curve and I want to subtract the bottom curve. And that will give me this y value, this purple height right here. So I'm going to have my top curve has a name, and that is f of x. And I'm going to subtract the bottom curve, which has a name, which is g of x. And that's what you're going to do when you have the area between two curves. So let's look at example 4. Example 4, we're finding the area of the region created by y equals x squared plus 1 and y equals x plus 3, and we're just going to write the setup. So again, the first thing that I always need to do is draw in my rectangle. So again, I need to make sure that I'm touching the red and the blue no matter where in the region I draw my rectangle. And I'm satisfied with this. So I go ahead and my width is dx and my height is y. So at this point, I know what my area is going to look like. It's going to have my bounds. It's going to have a dx right here. And then it's going to have the top curve, which the top curve in this case is the red curve. That's the top. It's the highest point on my rectangle, minus my bottom curve, which in this case is the blue curve. And I know that I need some bounds and that these should be x values here and here. So I don't have any bounds. It's not really all that pretty. I'm not really sure about them. So what I need to do is find my bounds. So to find my bounds, I need to know where is the blue curve. That's not blue. I need to know where is the blue curve equal to the red curve. That will give me my bounds. My blue curve is x squared plus 1. And I need to know, well, where is that equal to? Where does it cross my red curve, which is x plus 3. And from here, I need to solve for x. So solving for x, I'm going to go through this relatively quickly. I get everything on one side because I have a quadratic, and then I need to factor my quadratic. If you need a moment to do this, please take a moment and pause the video. I set each of my factors equal to 0, and these are my bounds. That's an equals 2. So I have x equals 2, so right here, this x value is 2, and right here, this x value is -1. So now I am able to plug in my bounds, and again, I had already decided that these bounds here and here in purple should be x values. I know that by the dx that's right here. So my lower bound is going to be -1, and my upper bound is going to be 2, and I know that my top curve, my red, is this x plus 3, and I know my bottom curve in blue is x squared plus 1. So I should be able to write my area is going to be from -1 to +2 of the top curve, x plus 3, minus bottom curve. I'm going to put the bottom curve in parentheses. If I don't do that, then I have to distribute that negative. And I multiply by the width so that I am sure that I have an area. So that is area between two curves. If you need a moment on this example, please pause the video here. Next one, we have draw in the rectangle that can be used for the Riemann sum, and what would this definite integral look like? So, drawing this one in, I can draw a Riemann sum angle like this. I'm not touching the red curve and the blue curve. So I have to draw my Riemann sum rectangle in like this, and again, wherever I happen to draw my rectangle this way, I have a width of dx, excuse me, that is not a width of dx. That's a width of dy, a change in y. And this distance here is an x. So for this distance x, I'm going to, instead of doing top minus bottom, I'm doing the rightmost, which would be the biggest x value. The rightmost x value is the biggest, and the leftmost x value is the smallest. So again, I'm always doing biggest minus little. That might be an easier way to remember it. We're doing big minus little. So in this case, I would have my area, it's going to be definite integral. The width of my rectangle is going to be dy. That tells me that my bounds here and here are going to be y values. I have one y value here is d, and one value here is c. I put the smaller one on the bottom, and the smaller one on the y-axis is the lower one, and the larger one is the higher one. Then I'm going to do the biggest x value, which is the right curve, which is in blue, which is f of y, and I'm going to subtract the smaller x value, which is the red curve, which is g of y. And that's how I'm going to evaluate the definite integral for this particular area. If you need a moment, go ahead and pause the video. For our last problem, we've been given our bounds, we've been given the two curves. So what I would like for you to do, I would like for you to pause the video, and I want you to draw on the rectangle, find your bounds. The bounds are already there. And then I need for you to set up the definite integral you would use to find that area. So please pause the video now. Here is my solution, and sorry, in this circle right here is my setup. If you are good with the setup, then have a wonderful evening and bring this completed video lesson with you to class. Walk into class and say, thank you so much, calculus teacher. I loved watching this video. Now, if you didn't quite get that, I'm going to walk everybody through it so you can just stay with me for a few more minutes. So basically what we have is we started here with the drawing of the rectangle. This is where I started. This is number one. So I drew in my rectangle, which has to be in this orientation so that I am touching the purple curve and the blue curve. That means that my height of the width of my rectangle is dy, and then the length is x. So from here I moved over to here. This is my step 2. I know that I have y values now going for my bound here and my bound down here because my width was a dy. Now, because of that dy, I also know that this thing has to be an x, but when I have x's, that means the variable I'm going to see y's. Okay, definitely going to see y's. Now, to set this up, I need to do the big minus the small, or the right side of my rectangle minus the left side of my rectangle. This is the large or big x value minus the smaller x value. And then what I need to do is I need to write my setup down here. So to write my setup, the first thing that I need to do is I need to identify my bounds. So the first thing I did was I plugged in my bounds, and to do that for my lower bound down here, I went over to this point here, and I didn't want the x value, I wanted the y value. So my -1 is what goes right here. Next, I needed my upper bound, and I went to the higher point, and that point is right here, sorry. I don't want the x value, I want the y value. So that's what I plugged in right here. Now I needed my leftmost curve, or the largest of the x values. And how did I get y plus 2? Well, I got y plus 2 because this was what my function was, y equals x plus 2. And what I needed to do was solve for x, because what I wanted in here was an x value. And I'm going to show you this thing needed to be an x value. But when I see that this has to be an x value, the variable I should see must be y's. So I come over here and I solve for x, and I did that by adding 2 to both sides. So that gave me y plus 2 is equal to x, which I had worked out down here at the bottom. So that becomes my purple big curve, and then I need to subtract my blue smaller curve. Well, when I went to my blue smaller curve, that function was x equals y squared. I already knew what x was. X was y squared. So I took y squared and I plugged it in right here. So if you have any additional questions, be sure you write something down. Don't just put a star, because a lot of students, by the time they get to class, forget what their question was, even though they write a star. So what you're going to want to do is, if you have any questions, go back and write them down, put a star next to it, but write your questions down so that you may ask when you return to class. So again, when you have a fabulous evening tonight, when you go into class, say, thank you, calculus teacher. I loved that video lesson. It was awesome. But most importantly, have a nice evening, and we will see you in class.